All right, in section 9.2, chapter 9, section 2, we're talking about more probability concepts. And I think this section's a lot of fun. We start with multiplication principle, which is also called the fundamental counting principle. I usually call it the fundamental counting principle of multiplication, FCP. That's just a quick abbreviation for it. It tells us that if a first experiment can be performed M ways, a second can be done N ways, then the two experiments in that order can be performed M times N ways. Now, when I'm choosing to use fundamental counting principle, I do this because I have more than one set of choices. So, well, let's just do some examples. If I'm in a restaurant and the special includes both an appetizer and a main course, that means there's two different lists to choose from. I have 3 different choices of appetizers and 3 different choices of main courses. How many meal choices are available? And it tells me to show an organized list. So let's just make up some options here. My appetizer can be a soup, it can be a salad, or it can be, what's a third appetizer? Oh my goodness, mushrooms, stuffed mushrooms. All those started with S. That's a pain. But those are my 3 appetizer choices. My main courses are going to be pasta, fish, or beef. Those are my 3 main courses. Very general today. So when I do an organized list, tree diagrams are my go-to, but we'll do what it says. We'll do an organized list. If I choose the soup, I can choose, I'm gonna do a tree diagram modified. I can do soup with pasta. I can do soup with fish, or I can do soup with the beef as my main course. So there's 3 different meal choices right there. Or I could pick the salad as my starter. And I could have salad with pasta, that's 1 meal. Salad with fish, there's a 2nd meal, or salad with the beef, there's a 3rd meal. So there's 3 meals with soup, 3 meals with salad. Can you guess how many meals there will be if I do the stuffed mushrooms? Stuffed mushrooms with pasta, with fish, or with beef. So there's 9 different meal choices. You see there's 9 different meals I could order? Well, if I use fundamental counting principle, I say, okay, I'm going to pick an appetizer and I'm going to pick a main course. There are 3 appetizers for me to choose from. There are 3 main courses for me to choose from. That gives me a total of 9 different meals I can order. Easy peasy, right? Just multiply the 2 sets of choices together. Now again, I have a set of appetizers, I have a set of main courses, so I have more than one set to pick from. Okay, all the clothes in my suitcase match because I packed really, really well. I packed 4 shirts, 2 pairs of pants, 3 pairs of shoes. Each shirts, pants, shoes counts as an outfit. How many different outfits can I put together as long as I consider changing my shoes a different outfit? Well, I've got more than one set. I've got shirts, I've got pants, and I've got shoes to choose from. Those are 3 different sets of things in my suitcase, right? I've got 4 shirts, 2 pairs of pants, and 3 pairs of shoes, which gives me a total of 24 different outfits that I can pick from what I packed. Fundamental counting principle. Okay, 2 roads connect cities A to B. 4 roads connect cities B to C. 5 roads connect city C to D. We're going to go through all the cities in order, A, B, C, D. How many different routes are possible? So let's look at a sketch of this one. If we start at city A, I've got 2, I'm going to go in this order, right? A, B, C, D. That's the way I'm going to take my drive. There are 2 different roads to get from A to B. 2 different choices. I can either take this road or I can take this road to end up at B. Then when I leave city B and go to city C, I've got 4 different routes. 1, 2, 3, 4 different ways to get from here to there. To get from C to D, I've got 5 different roads. There's a lot of different ways to get from C to D. So 1, 2, 3, 4, 5 different ways to get there. So like one route would be to take this road and then this road and then that road. That would be one route. Or I could take this road and this road and this road. That's another route. So you can see there's a bunch of different routes. But I'm picking 3 different times. I'm going from A to B, then I've got to get from B to C, and then I've got to get from C to D. So I'm picking from 3 different sets of roads. Well, there's 2 roads to pick from here, 4 roads to pick from here, and 5 roads to pick from there. So that gives me 40 different routes to drive. Okay? All right, how many different 4-letter radio station call signs can be made if the first letter must be K or W and no letter may be repeated? Oh, this one's fun. So we're doing a 4-letter call sign. So I've got 4 blanks to fill. Well, the first letter has to be K or W, so that's only 2 different choices. I don't have any limitations on the other 3 letters except that no letter may be repeated, no repetitions. Well, how many letters are in our alphabet? Do you want to remember? There's 26 letters in the alphabet. That's something you got to remember. There are 26 letters in the alphabet. And when you're doing digits, if you look at your calculator, you've got 0 through 9. That's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different digits. 10 digits. So good general information. There's 26 letters in our alphabet, 10 digits on our keypads. So if I've already picked one letter, either a K or W, and I can't repeat that letter, that means there's only 25 letters available for the next choice. And then I pick one of those, so there's only 24 letters available here, and then 23 letters available there. So if I plug that into my calculator and multiply that out, there are 27,600 different call signs available. That's a lot. It's more than we expect, right? What if I do allow repetition, but that first letter still has to be K or W? Well, in that case, I'm still filling those 4 blanks. I've got 4 letters to fill. The first choice has to be K or W, but then it could be 4 Ks or 4 Ws. I can do repetitions, so I'm going to use all 26 letters. They're all available to me for those other 3 blanks. So this is what I multiply through in my calculator. That increases my options to 35,152. And then my last setup says, okay, there's no repetition, and that last letter must be R. The first letter must be K or W. So 4-letter call signs, but that last letter I'm not actually picking. It's going to be R. The first letter has to be K or W, so there's 2 choices there. I've already used R. I've already used a letter here, so that's 2 letters used out of my alphabet. There's 24 letters left, and then 23, because there's no repetitions allowed. Let's plug that into our calculator. I don't have this one written down. 24 times 2 times 23. Order doesn't matter when you multiply, remember? You've only got 1,104 call signs available to you there. Okay, let's look and see what's next. Factorials. In factorial is a notation that you see with an apostrophe, oh my goodness, exclamation point, an exclamation point. And in factorial means that we start with whatever number we're given and we multiply our way down to 1. That's what this definition tells me. So for example, if I was given 5 factorial, this means I need to multiply, starting with 5, all the way down to 1. 5 times 4 times 3 times 2 times 1. If you plug that into your calculator, you see that that is equal to 120. Now, one thing to remember, by definition, 0 factorial is just 1. We use factorial when we talk about how to arrange objects. Well, if I've got 0 objects, I can arrange those 0 things one way. There's nothing there. Okay. Factorials, order of operations applies with factorials. So here, when I simplify, I have to figure out 7 factorial, I have to figure out 3 factorial, and then I subtract the 2. 7 factorial, I have a button for that, guys. Your probability button right here. If I do 7 and then do my probability button, I see I can move across to my factorial key. So 7 factorial is 5040. And 3 factorial is just 3 times 2 times 1. So I don't need to mess with my calculator for that. 3 times 2 times 1 is just 6. So this is 5040 minus 6, or 5034. Now, order of operations. Here, I need to simplify inside my parentheses first. 7 minus 3 is 4. And 4 factorial, I don't need my calculator for, but you can use your calculator for it. 4 times 3 times 2 times 1 is 24. And then again, do parentheses first. 12 divided by 4 is 3. And 3 factorial is just 3 times 2 times 1. That's just 6. Okay, order of operations. I can use my calculator for this, but I want to show you how to simplify so that you don't always have to depend on your calculator so much. 9 factorial means I start at 9 and I start multiplying my way down, all the way down to 1, right? 6 factorial means I start at 6 and I multiply my way down, all the way to 1. Let's go ahead and write it out the first time. What do you see has happened here? Well, I end up with a lot of factors over themselves. I've got 1 over 1 is just 1. 2 over 2 is just 1. I'm dividing out those common factors. 3 over 3 is just 1. 4 over 4, 5 over 5, 6 over 6. All of that gives me 1 because it cancels out, it factors out. And what I'm left with is 9 times 8 times 7. Well, that's pretty quick and easy to do in my calculator. 9 times 8 times 7 gives me 504. A quicker way to simplify this, to show how this simplifies, would be to say, okay, my numerator is 9 factorial, my denominator is 6 factorial, so I can stop when I get here because all of that is going to cancel out. So my numerator would be 9 times 8 times 7 times 6 factorial. And 6 factorial over 6 factorial, anything over itself is just 1. So I'm still left with 9 times 8 times 7, which is 504. Now, thinking about simplifying like this makes things a lot easier when we're given big problems like this. That numerator, 104 factorial, so if I do 104 and I find my factorial key, it tells me that is too big to calculate. Oh, we had a glare. Let me type that in again so you can see. 104 factorial, I hit my probability button and move over to the exclamation point. That's too big. My calculator can't handle that calculation. It gives me an overflow error. So what we do is we say, okay, well, my denominator is 102 factorial. So my numerator is 104 times 103 times 102 factorial. Anything over itself is 1. So what I really just need to calculate is 104 times 103, which we can do quick and easy in our calculator, 10,712. All right, what happens here? Well, I know that it's going to simplify and cancel out. Can I do that in my calculator? Well, let's look and see. If I do 29 factorial, it gives me an overflow error. What if I use parentheses? What if I say, okay, let's do parenthesis 29 factorial, close your parentheses, divided by parentheses 24 factorial, close your parentheses. There, the calculator works it out for me. So if I apply order of operations within my calculator, it gets me to that correct answer, and it doesn't freak out and tell me the value is too large. So I want to make sure you know how to simplify, able to show me how to simplify if I ask you to, but I also want to make sure you know how to use the calculator. Okay, the last two types of computations we're going to do in this section are permutations and combinations. Now, with permutations and combinations, the question is, does order matter? We have one type of calculation, permutations, where order does matter. And if I'm interested in arranging things in specific orders, I have more options available to me. That means I'm going to have larger answers. With combinations, however, order does not matter. So I'm able to divide out those duplicate groups because the order just doesn't make any difference. Okay, let's walk through this. Right here, this is important. With fundamental counting principle we had multiple sets to choose from. With permutations or combinations, there's only one set of things to choose from. I'm choosing from all the students in the room, from all the members of the club, from all of the players on the team. But that's just one set of options. Oh well, we'll go ahead and talk about it. Which one has more options? Well, if I only have two choices and order matters, VC isn't the same as CV. Those are two separate arrangements. If order matters, that's two arrangements. But if order doesn't matter, VC is the same thing as CV. It's the same, so that's only one arrangement for a combination. So when order matters, I look at these as two separate outcomes. Well, if the order doesn't matter, this is just one outcome. Okay, I've already made an organized list for you of all possible arrangements of the four letters A, B, C, D taken three at a time. So I can do ABC, ABD, ACD, BCD, ACB. You can see I put it together. I promise that's all of them. All possible arrangements of A, B, C, D taken three letters at a time. So I have four letters. I picked three. If order doesn't matter, well, if order does matter, I've got 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4 rows. 6 times 4 gives you a total of 24 possibilities when order matters. And order matters, that's permutations. So if I have four things and I do permutations of three of them at a time, I get a total of 24. Order matters. But what if order doesn't matter? We're going to use different colors to group together combinations that include the same three letters. I want you to pause the video and try this after you see what we're doing. So right here, I'm going to use pink to mark every time I see A, B, C together. So A with B and C, right there and right there, right there, right there, right there. Is that it for A, B, C? So we've got pink is A with B with C. I will do green with A, B, D. A, B, and D together. You see, I found 5 more options. Oh, look at that. There's another ABC. There's another pink one. ABC, there's 6 options. There's ABD. So there's 6 in pink, 6 in green. 6 of ABC, 6 of ABD. I will do purple for ACD right there. 1, 2, 3, 4, 5, 6. There's those 6. And I will do blue for B, C, D. 1, 2, 3, 4, 5, 6. So I only had a total of 1, 2, 3, 4 different combinations of those 4 letters. So when I took my 4 letters and I did combinations, where order doesn't matter, 3 at a time, I only had 4 different options instead of 24. When I did permutations where order matters, I had 24. When I did combinations where order didn't matter, and I grouped them together by color, I only had 4. So, permutation or combination, when we're trying to decide, we know that if we've only got one set, it's going to be one of these two, and we're going to watch for keywords that let us know whether or not order matters. Alright, let's do some examples of these. Greek alphabet has 24 letters. How many ways can one name a fraternity using 3 Greek letters with no repetitions? Well, I've only got one set of letters, one set, so it's either going to be permutations or combinations, P or C. If I'm naming a fraternity, does order matter? Well, yeah, with a name, order absolutely matters, right? So order matters, that means it's going to be a permutation. So I've got N, pick R, and the other side of the page gave me my formula for that. The other page, let's see, permutations. My permutations formula is right here. I do n factorial over n minus r factorial. So I've got 24 letters total. The n is my total. I'm picking 3 at a time. So I've got 24 factorial over 24 minus 3 factorial. So that's 24 factorial over 21 factorial, which remember we showed how to simplify. Where can I stop? I can stop at that when I match the denominator, right? So 21 factorial, that cancels out, and I'm left with 24 times 23 times 22, which is 12,144 different things to name my Greek fraternity or sorority. Quick and easy. If I'm doing permutations and I know I've got 24 pick 3, I know that's going to divide out. So I can say, oh, I need to fill in 3 blanks because I'm picking 3 times. The first time there's 24 options and I count my way down. 24, 23, 22 gives me that answer. And I don't have to go through the full formula. How many ways can a merchant with limited space display 4 different fabric samples side by side from her collection of 8? So how many total does she have? Well, she's got 8 total, so that's going to be my N. We're going to display 4 of them, so that's my value for R. And we have to decide, does order matter? Well, if you arrange things, if you care about how things look, order matters, right? How they affect each other side to side. So we are going to say that yes, order matters. We've got one set of choices and order matters. So that's permutation. We've got 8. We're picking 4 of those 8. So for the first spot, there's 8 options. For the second, there's 7, and then 6, and then 5, which when I multiply my way through, I've got 1,680 different arrangements available to me. Alright, how many ways? Oh, 4 items are randomly selected from the first 25 items on an assembly line in order to determine the defect rate. So we've got one set of items on the assembly line, one set. And so now we have to decide, okay, it's going to be permutations or combinations. Which one? Does order matter? 25 items total. We're picking 4 of them. We're choosing 4 of them, so that's my R. Does order matter if we're checking for defects? Well, no. We're just going to get 4 of them in a group and then evaluate them. So we've got 25 items, choose 4. And if you look back at your formula for combinations, it's just like the permutation formula, except then I divide out the duplicates by using that r factorial in the denominator. So if I want to set it up as according to the formula, I've got n factorial over n minus r factorial times r factorial. So I've got 25 factorial over 21 factorial times 4 factorial. I know that the 21 factorials are going to cancel, right? So if I want to show how to simplify, I can do that. What if I don't need to show how to simplify? Well, let's go ahead and show this one more how to simplify. So we're going to start here. We're going to say 25, 24, 23, 22, and I get to that 21, and that 21 factorial is going to cancel out. But I also have 4 factorial in my denominator, so that's 4 times 3 times 2 times 1. So in my numerator, 25, 24, 23, 22, divided by 4 times 3 times 2. Well, that's divided by 24. I end up with 12,650. So if I tell you to show me how to simplify, this is what you need to show me. What if I don't tell you to show how to simplify? Well, if I don't tell you to show me how to simplify, you can use your calculator and your probability button. I've got 25, move over to combinations of 4, enter, and there's my result. So know how to simplify in case I ask you to simplify for me, but also know how to use your calculator. All right, a manager must select 4 employees for promotion. There are 12 employees of equal tenure and ability that are eligible. So it sounds like they're all on the same footing. They're going to up for the same promotion. So we've got one set of employees. Does order matter? Not if they're all up for the same promotion. Order doesn't matter. So that means it's a combination. The whole group is 12. We're going to choose 4. We can set it up using our probability button. 12, choose 4. Gives me 495 ways I can select 4 employees for that promotion. Now things get a little bit more complex, but not really. Our football team has both juniors and seniors playing on the team, 8 juniors, 11 seniors. We're going to select a group of 4 co-captains. We want 2 of them to be juniors and 2 of them to be seniors. How many different 4-person groups are possible? Well, I need to look at this as, first of all, does order matter? And it doesn't. Co-captains is the same position, so order doesn't matter. So we're doing combinations. The thing is, we're doing 2 different combinations. So we have a combinations with juniors, and then we have combinations with our seniors. And we're going to multiply that together. Fundamental counting principle says when I have more than one set, I multiply the number of options in each set together. So we're doing fundamental counting principle with our combinations. Combinations because order does not matter. Juniors, we've got 8 juniors and we're going to choose 2 of them. Seniors, we've got 11 seniors and we're going to choose 2 of them. So if I plug this into my calculator, 8 choose 2 gives me 28. 11 choose 2 gives me 55, for a total of 1,540 ways to select those 4 co-captains. That's a lot, huh? All right, just a few more and then we will be done with this section. From a group of 15 smokers and 21 non-smokers, so we've got 2 sets, so we automatically think, okay, we're going to have 2 different blanks to fill. A researcher wants to randomly select 7 smokers and 6 non-smokers for a study. Now they're just in a study. Once they're in the study, it doesn't matter what order, who is picked when, does not matter. So we've got more than one set, so we've got fundamental counting principle. But within each set, we've got to make a selection where order does not matter. So those are going to be combinations within each set. So we've got a set of smokers, and we've got a set of non-smokers. How many smokers? Well, we've got 15 smokers, and we're going to choose 7 of them. We've got 21 non-smokers, and we're going to choose 6 of them. And then we're going to multiply those values together. So if I do 15 choose 7, I've got 6435. And notice that I am showing you step by step. You need to show me so that I know what you did in case things went wrong. I know how close you got. And then this one is 54,264. And I've got to multiply those 2 amounts together to get the total number of ways they can pick people for the study, which is 349,188,840. Okay. How many ways can the letters in the words Fort Worth be arranged? Now, I have to divide out the duplicate letters. When I'm arranging things, arrangement implies that I've got a specific arrangement where order matters. Order matters, but I'm going to divide out the duplicates. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. I'm going to arrange all 9 letters. Order matters, so that's my 9 factorial. But I've got to divide out the duplicate letters because an O is an O is an O. I can't tell if that's the first O or the second O. speaking of, I've got 2 O's, so I'm going to do a 2 factorial to represent those repeated O's. I've also got 2 R's, so I'm going to do another 2 factorial to represent those repeated R's. And I have 2 T's, so I'm going to do a 2 factorial to represent that repetition as well. Well, my numerator is 9 factorial, which is, oh dear, my battery's running low. 362,880, 362,880. And I'm going to divide that by 2 factorial times 2 factorial times 2 factorial, which comes out to be 8. And this gives me 45,360 ways to arrange those letters in Fort Worth. Okay, so we are going to, you guys are going to give me just a second. We're going to hope that we don't mess up our video. If we mess up our video, we will come back and do a second video. I can't plug it in. Okay, let's get through this next 2 examples. If we don't get through the next 2 examples in this video, you'll have to see it in class. And how many ways is it possible to answer a 6-question multiple choice test if each question has 4 answer choices? Each question on my test has a different set of possible answers. 1, 2, 3, 4, 5, 6 questions. First question, second question, third question, etc. And each question has 4 answer choices. It's fundamental counting principle because each question has its own set of choices. So I'm multiplying 4